In this video, we're going to define what we mean by a Euclidean domain. Informally, a Euclidean domain is basically a domain that has some kind of a generalized division algorithm in it. And so what I want to do is I want to look at the two rings that we know have nice, well-behaved division algorithms. The first one, of course, is the integers. And the usual way of stating the division algorithm in the integers is as follows. If a is an integer and b is a natural number, we can find integers q and r such that a is equal to q times b plus r, and r is bigger than or equal to 0 and strictly less than b. The problem with this version of the division algorithm is that it does not allow me to divide by negative integers, but it's easy to patch up. And so I want to look at the more general version for the division algorithm for integers, which is usually stated as follows. If a and b are any integers and b is not 0, then we can still find integers q and r such that a is equal to q times b plus r, and this time r is going to be trapped between 0 and the absolute value of b, because this allows me to let b be a negative number. Now, it's important to also understand that this constraint on r is just a formal way of saying that the remainder is going to be smaller than the divisor b. Well, now let's look at the ring of polynomials. If we happen to have f is a field, then the ring of polynomials where the coefficients are drawn from f always has a division algorithm. And the division algorithm for f square bracket x can be stated as if f and g belong to f square bracket x and g is not equal to 0, then there exist polynomials q and r in f square bracket x such that f is equal to q times g plus r, and r has to satisfy these two constraints. The degree of r of x is strictly less than the degree of g of x, or r of x is identically equal to 0. Now, it's important to understand that this part of the way I'm stating the division algorithm for the ring of polynomials is slightly different than how the author stated the division algorithm for polynomials back in chapter 17. But it has the advantage that this or means that we can now define the degree of the zero polynomial to be equal to 0 if we want to, because if we are dividing by a constant polynomial, so if I have g of x is identically equal to a constant polynomial, then f of x is nothing more than 1 over c times f of x times g of x plus 0. And we've got the degree of g of x is equal to 0. And of course, the degree of the remainder is equal to 0, but because of this or, it doesn't matter that this first equation is not satisfied. It doesn't matter that that particular inequality is not satisfied because this particular provision is satisfied. The other thing that's important to realize about this condition is that essentially this is still saying that the remainder is in some sense smaller than the divisor g of x, or of course g of x actually divides f of x. And it's this idea that we want to try and capture in a formal definition for a Euclidean domain. So now we're ready to actually start thinking about what is a Euclidean domain. Now, we're going to actually introduce one new Greek letter, and I want to go ahead and get this written nice and properly for you, because it's very irritating when a math professor throws in a new Greek symbol and doesn't really tell you what it is or how to write it. We're going to be using a funny looking V shape, and this is the lowercase Greek letter nu, which is in English spelled in U. And nu is going to be a function from our domain to the non-negative integers. So the formal definition of Euclidean domain looks like this. We're going to let D be an integral domain, and we're going to call D a Euclidean domain or an ED for short, if and only if we can find a function nu going from D to the set of non-negative integers, which can be written as in union with the set containing 0, that has the following two properties. And the first property is, for non-negative elements A and B inside D, nu of their product has to be bigger than or equal to nu of each of the factors. So nu of A times B will be bigger than or equal to nu of A, and likewise nu of A times B will be bigger than or equal to nu of B. Now this has only got to be true for non-negative A and B's. The second property is the thing that looks like a division algorithm. For A and B inside my domain D, and B is something other than 0, we can always find R and Q inside D such that A can be written as Q times B plus R. And the second thing is that we have that nu of R will be strictly less than nu of B, or R will be the 0 element inside my domain D. Now it's important to understand that what this second piece of stuff is saying, in other words, this stuff here, is basically saying that R is somehow smaller than the divisor B, using nu as the measure of size inside our domain D. And here again, it turns out that under certain circumstances, if nu of B happens to be equal to the same thing as nu of 0, that's going to force the remainder to actually be equal to 0 here. So this is basically saying that if B doesn't divide A, then the remainder has to be strictly smaller than the divisor B, under this notion of nu being what tells us the size. Now, to finally end this video, I want to go back to our previous rings and look at the nu for those particular things. But I guess before I do that, I should say one more thing. We have one more silly little definition. We call nu a Euclidean evaluation on the domain D when we happen to have a Euclidean domain. And the last thing that I want to do in this video is I want to go back and look at the Euclidean evaluations for the rings that we already know about the division algorithm in. So if we go all the way back to the integers, this thing right here says that nu on the ring of integers is just absolute value. So nu of any k is just going to be the absolute value of that k. And it turns out that nu will have both properties. And then if we look at the division algorithm for fields, this stuff here says that nu on f square bracket x is just degree of the polynomial. In other words, nu of p of x is just going to be the degree of p of x.